previous lecture we see that the surface and volume integrals of the vector field. Surface integral, consider a vector field and surface S in the field. It is assumed to be continuous. Let V bar is the vector at a point P on the surface and unit vector N bar at a P perpendicular to the small area element ds about the P. Let V bar is equal to V1 I cap plus V2 j cap plus V3 k cap. Then V bar dot n cap ds is equal to V bar dot ds bar is called the surface integral of the vector field over the surface S. Here ds bar is equal to n cap ds. Then now if we consider the projection of S in the xy plane, it is denoted by the r, and the projection of xy plane is a ds is equal to dx dy. Then k cap into n cap ds is equal to dx cap ds bar is equal to dx dy. Integral over s is equal to v bar dot ds bar is equal to v bar n cap ds is equal to v1 I cap plus v2 j cap plus v3 k cap into n cap dot ds. v3 k cap n cap ds is equal to v3 dx dy. v1 I cap into n cap ds is equal to v1 dx into dy. v2 j cap into n cap ds is equal to v2 dx into dz. Volume integral. If S is a closed surface enclosing a volume V in a vector field, then A bar is equal to x, y, z. Then integral over A bar dot dv is called the volume integral of the vector field A bar over the volume V. Then next, Gauss divergence theorem. If f bar is a continuous differentiable vector point function and S is a closed surface enclosing the volume V, then divergence of the f bar dv is equal to integral over S f bar n cap into ds, where n cap is a unit vector normal drawn outward. In the other word, it is a volume integral of divergence of the vector function f bar over a closed volume V is always equal to the surface integral f bar over the closed surface S enclosing that volume. Let a function f be defined in the Cartesian coordinate system. F bar is equal to f1 x cap xy z I cap plus f2 j cap plus f3 k cap. f1 f2 f3 all the functions of the xy z and their derivative are assumed to be in the uniform, finite and continuous in all directions. Suppose S is closed surface such that any line parallel to the any coordinate axis cut it at the most in 2 points. Consider the intersection of the surface S by the line parallel to the z axis. Let the z coordinate of the point z1 is equal to f1 xy and z2 is equal to f2 xy. Therefore, the upper and lower small portion S1 and S2 of the S about the 2 points are given by f2 xy, z, f1 xy respectively. Then divergence of the f bar del v, integration of the v over dou f by dou x plus dou 2 dou f2 by dou y plus dou 3 by del z divergence. Then f1 x dv, integration of f2 del y plus dv. Then z1 z2 del f3 by del xy z dx dy, where r is the projection of the s in the xy plane. Then integral over the f3 x1 y1 f1 minus x1 y1 f2 dx dy. Integral over r is equal to f3 x1 y1 f1 dx dy f3 x1 y1 f2 dx. Now the portion s1 we have dx k cap n1 ds1 since n1 cap is directed upwards and for s2 vy as a dx dy minus k cap n1 cap ds2 since n2 cap is a oppositely. Del f3 del z dx s1 f3 k cap n1 ds1 plus integral over s2 is equal to f3 k cap n1 n cap into ds2 f3 k cap n1 ds1 plus n2 ds2. Then integral over the f divergence of the f bar dv is equal to integral over s f bar n cap ds is equal to, hence it is proved.